So yesterday metallurgy chapter, some people had asked raised doubts.
The Vesper theory. A Vesper theory,
Froth
break it
flotation.
down into 5 points, and remember the first point is, go to your textbook also, you'll find it, but it will be in long paragraph forms. You remember
Furnace,
these
froth flotation, then
basic points.
magnetic
First
separation.
is treating the electron as a charged cloud instead of a single particle.
Which topic you said you have doubt?
So in Vesper theory, it was
Froth flotation and
introduced
furnace.
by
Froth flotation,
Sidgwick
furnace,
and Powell. Sidgwick
somebody
and
else
Powell
has-
introduced Vesper theory, and then it was developed by Gillespie and Nihom also. 4 names. Gillespie, Nihom, developed it further, introduced by Sidgwick and Powell. After that, what is the theory? First point, as I said, it is to consider the electrons as charged
First,
clouds.
metallurgy.
Electrons are very small,
What is
very
the
fast
difference
moving
between
particles. They
mineral
move at the
ore?
speed of light, so it's almost impossible to spot the
Mineral and ore. What is
electron
the difference between
at any
mineral
given
and
particular
ore?
time. Exact position we cannot say. So that is why the area in which it revolves or where it can be found, it is known as a charged cloud. These clouds, when
No one
they
knows.
interact, two clouds come together, what happens? Because they are negative, definitely repulsion
What is a mineral?
takes
What is
place.
a ore?
Negative charges repel, so these also repel. So these charged clouds, they behave like
Basic definition I'm asking, nobody is able to answer.
areas of
Ma'am,
charges.
ore is the combination of mineral and some of the
The central
impurities.
atom. The central atom,
Hmm.
around it, that is central atom means beryllium. If we are
So what is
taking
mineral?
beryllium's the inner core, which is not participating
There
in
is
the
one
reaction,
question in the text.
that becomes the central atom. The two chlorines which are
Every ore
BeCl2
is a
formation, the
mineral,
two
but
chlorines
not
which are
every
coming
mineral is
towards the
ore.
sides,
Justify.
what will be at the center?
This is there in
Beryllium.
the
So beryllium
first,
at the
second,
center
third.
is central atom.
First page or second page.
Around it, whatever are
below
there,
that.
if we know that whether it has a
That
bond pair,
blue
a
color
lone
shape
pair,
part
how
questions
many
will be
bond
there.
pairs, how
It is
many
there. It's
lone
not at the
pairs.
back in theory you're learning.
We know this, we can predict the
Middle of
shape
the
of the atom.
lesson only. Starting.
Molecule,
First
sorry,
or
not
second
atom.
page, this question will come.
If we know the
It is
number
an
of
important
bond
question.
and lone
Justify
pair around the
how
central
we can
atom,
say
we
that
can predict
every
the shape of
ore
the atom.
is a mineral, but not
The
every
next thing is
mineral is an ore.
the atom. If it has
So what is a metal
all
crystal?
bond pairs, then the repulsion will be equal among them. So bond pair, repulsion only will be. Now if there is one pair of electron which is
You have
not
been studying
bonded to
chapters
anything
blindly.
else,
So what
no
will
binding,
happen?
that is called a lone pair. The lone pair
When
and this bond pair,
we have to
two bond pairs are there. The repulsion
answer
between them
objective
will
questions
be
pertaining
less
to
than
such
the
topics, it
repulsion
will become
between the
difficult,
bond
we'll get
pair and the
confused.
lone pair.
So it's
lone pair
always
bond pair repulsion is greater
means we
than
should
lone
always
pair
know
bond pair
what is
repulsion. The last is
the base of the
lone
chapter
pair
we are
lone
studying.
pair repulsion. There are two lone pairs. Repulsion between them
Furnace you didn't
is
understand,
maximum.
we can explain, but when you don't
So lone pair
understand
lone pair
terminology,
repulsion exceeds lone pair bond pair repulsion,
clarity won't
which
be
is
there.
more than bond pair repulsion.
We are saying metals and non-metals. These are all elements.
Knowing this, we
In
can
chemistry we have
predict the structures of
around
molecules.
120 elements today.
So these are the 3 points. One is
These elements,
it is treated as a
those
charged
which
cloud.
show
Second one is by
certain
knowing the
properties.
number of bond and lone pairs across around
Those
an atom,
are
we can
called
predict
metals. Which
the shape of the
properties?
atom. Third is how the
Eighth class
repulsion
you
works.
studied.
LP greater than LP
Last
greater
year.
than BP. The next 2 points are about
Malleability,
shapes of atoms.
ductility,
Shapes of atoms. First
sonority,
we have beryllium chloride and
conduction
boron
of heat,
trichloride.
conduction of electricity.
BeCl2 BF3.
Basic 6 properties
CH4
were there.
methane.
In each class you studied these 6.
Actually,
Should
carbon
be
dioxide
sonorous,
also you
means
can
when we
measure
hit it,
carbon
you should
and
get a ringing
this
sound.
side oxygen.
Should have
Because
luster,
there are
shiny,
no lone pairs. there.
ductile
Carbon
and
has 4
malleable.
outer
It
bonds.
should be made into a sheet. It should be
Each one gets 2
possible
bonds
to
to
make
one
it into a
oxygen,
wire.
2 bonds to another oxygen. So
Ductility.
CO2 is C,
Then
double bond
it
O
should
this side, double
conduct
bond
heat
O
and
that side.
electricity.
So it's a
These
180 degree
properties,
linear
if
molecule, straight line
that element
structure.
satisfies, then it's called
This
a
way,
metal.
We can
Those which do not
take any
satisfy these
molecule and
properties, we are
explain
called
its shape, but
non-metals.
you have these 5:
Now,
beryllium chloride, boron
metals or
trichloride,
non-metals.
then
Non-metals is
water,
in the form
ammonia,
of gases. Some of them are there.
CH4, methane.
All metals are either, they are all solids except one,
If
mercury,
anything
which is a
else is there,
liquid.
then
Everything
it will
else is
follow the
found in
same
solid
rules.
state.
Whichever
So
is there,
generally
it follows
non-metals
these
only we
same
get
rules.
in
It does not have
gaseous state.
anything different from this.
So they are found
One more theory is valence
above the Earth's
bond
surface
theory,
also.
VB theory.
The Earth only. Earth does not mean only the
That
ball
is
which is below you.
formation
It's
of
also
N2
the
molecule, formation of O2
atmosphere around
molecule.
you.
They
Air.
come in this. How does
So
oxygen
air gases which are there,
form? O2
there
molecule, how
we'll
does
find
it form?
non-metals. Some non-metals are
How
found
does
in
O2
water.
molecule form?
Some are found in the earth only.
Each oxygen
But
has
almost all
1s2,
metals are
2s2,
found in the
2p4.
earth only. So extracting
So
that metal from the earth through proper processes,
1s2, 2s2, 2p4 it has.
that
So
is
when
called
it has
metallurgy.
1s2, 2s2,
The
2p4,
science of extraction of the metal. This metal, because it is
in
buried
2p,
under the earth,
2px will have 2
it
electrons,
is,
2py and 2pz will have
the
1
metal will
electron
be there.
each.
It's like
So
mixed up
the
package.
2py, 2py,
Metal is there.
2pz, 2pz.
If it
Two
is
oxygens.
non-reactive metal, that means it does not
Repeating.
react with other substances
Each oxygen
present in
has
the earth,
1s2,
then it
2s2,
will be
2p4.
found in
Two such oxygens.
dirty form.
So
Like it might be
in
wrapped up
2p
in
orbital,
mud
2px, the
and
first orbital will have 2
say
electrons.
clay, sand.
2py will
These
have
things
1
might have
electron.
covered it. That
2pz
is one
will also
possibility.
have 1 electron.
So if you
2py
just
and 2py of
wash away that
oxygens, two
impurities,
oxygens,
we will be able to
2pz
get
and
the pure.
2pz of two oxygens will
But if
bind
the metal is
together,
reactive,
creating a
it's
double
chemically
bond.
reactive. So
Last bond
it
which
will
forms
not stay in
2pz,
its pure
2pz,
form.
which forms,
It
that is
combines
called
with
the
those
sigma bond.
elements
First one which forms, that
chemically.
is corner,
As if you have
that
magnesium.
is called the
It's a
sigma
metal.
bond. First bond
It's
between
a
two
reactive metal.
atoms.
So this metal will react
Next
with oxygen,
bond which forms, that is
hydrogen,
called a pi bond.
water,
Pi bond is a
chloride,
weaker bond. This is the
nitrites,
second bond which forms.
sulfates,
Now
whatever other
both oxygens
elements are
p
present in
orbital
the
is
earth,
dumbbell
it will
shape.
react with them.
So when
It
two
will form
dumbbell shape
different
come and collide
compounds.
like this,
Now
this is already
first
collided, bond is
they
formed.
form these compounds.
The other
Then
dumbbell
this
is vertical.
compound, because
P
it is buried
orbital
under the
is,
earth, it
one
will be
is like
surrounded
this,
by
the other one is like this.
dirt, dust,
So the vertical
sand,
dumbbell of both,
stones.
when they collide, they
These
cannot
all will
collide
come.
directly head on hand. Top
It
and
is
bottom
also
only will
possible that
bind.
in the same
So the
area
bond is partial bind.
we have
Partially
magnesium
up
deposit,
and
we have
partially
calcium
down.
deposit. That
Central
means
PP will
magnesium,
overlap
calcium,
like
both are
this.
there. Both
Top and
metals
bottom
are present.
partial bonds will form.
Both these
So
metals
it
are
is a weak
reactive
bond.
also. So magnesium
This
will
is
react with
called
something and forms a
double
magnesium
bond of
sulfate.
oxygen. One is
Calcium
this
reacts with
end-on-end
sulfate and
bond.
forms calcium sulfate.
Top and bottom overlap
They
is the
both
second
also
bond.
together they
So
might
two
be
bonds,
wrapped
one
up in
pi, one sigma.
dust, etc. All
If you
dirt
take
might be
nitrogen,
surrounding it.
in nitrogen we have 1s2,
This, when you
2s2,
extract the earth, we
2p3.
will get this whole thing. The entire
So
package
all the
will
three
be
p
there.
orbitals have single electrons.
This is
The last one,
mineral.
2pz will overlap
This what we are
directly,
getting directly
forming
from
sigma
the earth.
bond.
This is called the mineral.
Previous one, 2py will
From
overlap
this,
sideways, that is up and down, and
what
form
we
pi
obtained,
bond.
say it is
Another
about
2px,
80% of
2px
it
also
is
will
magnesium
overlap
sulfate.
sideways and form another pi bond.
15%
It
is
forms
calcium
one
sulfate,
sigma
remaining
and
5% is
two
some
pi
other
bonds.
metals.
The formation of oxygen
Now
and
we will apply our processes. Whatever process
nitrogen.
we are doing, all require
Oxygen and
some machinery,
nitrogen
some effort, some human beings
formation.
work.
These
So
come
they
under
involve
valence
cost.
bond formation.
It is not done freely. It requires machinery, it requires people to work on it, means it requires us to spend money. So from this you will extract magnesium, you will do your hard work and get, on what will you focus? 80% of it is magnesium. So will you try to extract magnesium or 15% of calcium or 5% of the other metal? Where will you spend your money? So we might be trying to extract magnesium from here, because whatever output we get, say you spend 10,000 rupees and finally you are able to separate the magnesium there. Once you separate the magnesium, It's a series of chemical process. First physical process will be there, then chemical process. Physical process, chemical process. The difference I'll come to it later. For now, understand there are types of process. So you apply all your process and you have separated the magnesium. Once the magnesium is separate, you will sell it. It's a metal. So as an industry, you
Atomic
will
number
try
of
to sell that
oxygen is
metal.
8.
When you sell the metal, at least you should earn more than the 10,000 you
So
spend.
1s2, 2s2, 2p4.
If overall you are selling the magnesium for 5,000
2px
rupees,
has 2,
will
2py
you
has
even
1,
go
and
for this
2pz
process?
also has 1.
Will you try to do this process? By spending 10,000, I am only going to get worth
So if you
5,000.
take
Will you then
its
invest in the process?
No,
follicular diagram, it is
Why?
like this. Now this red
we are
ones
going
are
to
the
get
px,
lost.
px horizontal. So
Economically
when they come close together, they
not
will directly
feasible.
overlap.
The terminology in textbook is economically feasible. That means you should earn proper
This
profits
is
there.
called sigma bond,
It should
direct
be
overlapping,
the
each one
process
coming
should
on to each
get
other.
some profit in the end.
The top and bottom
So
direct overlapping is not possible.
say
So
this is one ore.
sideways they
One ore,
just come close
10,000 you
together.
spend, you are
That
getting
bond,
worth
the
rupees
top and
5,000.
bottom, is known as
Another ore is there
pi bond.
for which I
So
can
there is
use
a
cheaper
partial
ways
pi
to
bond on top
extract
and
the
half
metal.
at the bottom. So partially two
Here
bonds will
say it
form.
was magnesium
That
sulfate
is
and
the pi bond.
it
Oxygen
went like this.
molecule
10,000
forms
if I
like
spent,
this.
I am able to earn only 5,000. Suppose I have magnesium
Similarly,
oxide
we'll
ore.
see
If I spend 2,000 also,
formation of
I
nitrogen.
will get metal worth 5,000. So instead of spending on this magnesium sulfate, I will invest my effort on that 2,000 rupees process. That metal I will work. So that part which we got, that is called an ore. Ore is that from which we can profitably or economically extract the metal, from which we can earn some profit. That mineral is called an ore. The mineral from which it is not possible to extract with a profit, that remains a mineral only. Okay, one of the mineral, classic mineral is sand. Sand is silicon dioxide. It's a combination after that, but basically it is silicon oxide.
Electronic
Dioxide.
configuration is 7, 1
But
s2,
from
2
sand,
s2,
extracting
2p3,
silicon is a
3
very difficult process.
unpaired electrons.
Silicon is extremely valuable. All our chip, computer chip, your SIM card, that internal memory, everything is
This
made with
2px
silicon and germanium.
and one more nitrogen
Memory chips,
2px.
IC,
They
integrated
both
circuit.
will collide
But
directly.
process of extracting silicon, people don't take sand and extract it because it's a very difficult process, very costly process, and not profitable.
Forming your
So although
sigma
sand
bond.
is
So
widely
2px,
available,
2px, when it overlaps, we
we
get a
still
sigma
didn't
bond.
get a
So
mechanism
this
or
two, the
method by which
vertical
we can
ones,
extract the
this
metal
vertical one and
with
this
profit.
vertical
It's
one
a very
will form a
difficult
bond.
process.
This
So
side
till now
tilted
sand is
ones
taken
will
from
form
other
the second
sources,
bond.
not
So
from
remember
sand.
to draw a line
Sand is a
between the
mineral,
top half of
but
this
not an ore.
tilted one, bottom
Ore
half
is
of the
that
tilted
from
one,
which we can profitably
and another
extract.
line
So
between
this basic difference we
this
should know
vertical top half,
between
vertical bottom
metal
half.
is what we are going to get end product.
So
This
this
metal
we
is
have
present in
3 bonds
minerals.
of nitrogen.
Mineral will become an ore when it is economically feasible to extract. This ore, for every metal, because it combines with some other
So this is
metals or
how
non-metals.
valence bond
Inside
series
the earth,
oxygen and
one particular
nitrogen
metal
forms,
will
and rest
combine with
was
other metals
rest of
or
the bonds are
non-metals.
formed.
Okay. So it will be in fused state. So after combining also, it will again get wrapped in dust, dirt, etc. That is this mineral or ore which we have. From there, we follow a certain series of steps to finally get the metal. This is metallurgy. First step, three process according to our textbook. First is extraction. Second is refining is third process. No, reduction. Third one is refining. Reduction of the ore, and third one is refining of the ore. So there will be one hierarchic chart in your textbooks. Which process we can continue to give what first? Low reactive, mid reactive, high reactive, then process names, and then steps will be there. What process can be applied under each. If you know that, that is a summary of your whole chapter. In this first job, see, we will identify the ore. Means we will know that from this we can extract profitably. So in tons will be taken out from the earth. Because it comes from earth, whatever it is, it has to be cleaned. It is the external physical impurity that has to be removed. That involves physical processes. For physical process, chemical reactions are not really required. Simple methods can be used and the outside coverages can be removed. Outside coverage, when I mean, it is basically dust, dirt. So that involves four processes: hand picking, washing, froth flotation, magnetic separation. First extraction of ore, that is dressing or concentration, that involves four processes. That is, there are many processes. We are learning four of them. Okay. In this four, what are they? First one is hand picking. You want to clean something. Clean. If I say cleaning, what all methods come to your mind? Say you have to clean your room. What all methods we have? What methods you will use to clean your room? Sweeping. One he said sweeping. Then if you are unable to mute and answer, at least type. You have chat there. Dusting. Removing the waste. Yeah, right. Next. Mopping, wiping. Okay, now see, with any one process, can you complete cleaning your room? You gave me five different answers here. With any one single process, can I complete cleaning my room?
No.
No. Just a dusting, not possible. It will just gather, I mean, from the surface, it will remove the dust, but dust will go and fall somewhere else. Even if I make sure that all the dust goes to one particular place also, I still have to remove the dust from there by either sweeping or by wet mopping. Something I have to. Then separation is very important. Removing waste material, what you say. When you are dusting, you might come across something which you don't require. So just by dusting, you can't remove it. You have to physically take your hand and separate the particle from here and there. So depending on the kind of impurity or the kind of dirt involved, you are applying methods. Now, some liquid has fallen. Definitely, out of these, we will use only mopping there, or maybe wiping. You will take a cloth and wipe. Both are similar, but depending on the kind of the impurity or the dirt involved, you are applying your method. That is what is done here also. Depending on the kind of impurity or kind of separation required, we will take our methods. So first one is hand picking. It's a very simple method. How do you clean rice or dal at home? Why do you clean rice or dal first?
It contains some stones.
Maybe it contains stones or maybe worms or something. So how do you clean it? By water. Water is second. Water is second process. First, what do?
Picking the stones.
You pick it up. So it's easy to pick it up and throw it because one is white and one is mostly not white, either black or it's not the same as rice. Even if the stones are white stones, shape is different. So the impurity differs from the main thing by shape or color. Shape, size, color. So the ore, the metal, and the impurity, or the ore and the impurity, they differ by either size, color, or shape. And this is, you might have seen during construction process, few women will come and will sort out the sand they'll bring for construction, and then they'll have one big net like thing and they'll throw sand on it. They'll separate. While separating, one woman will sit there and she will pick up the large stones and throw it off. That is hand picking. She is separating the required ore and the impurity by hand picking. So hand picking is this only: when the ore has impurity of large size or of different color, literally it is picked and thrown away. That is hand picking. Second one is washing or hydraulic washing. Here it is, we take something which is dissolving in water. Now we wash. When we know that it's your shoes got very dirty, we wash it. Tires, we wash it. Why do we wash it? Because we know that the mud will flow away in water. Mud will flow away in water. This one, because it's heavy, it will stay there only. Mud being lighter, when you pour water on it, it gets carried away by water. So water has the tendency to flow with the lighter particles. So when the impurity is less dense, means it can be carried by water, or the ore can be carried by water. Anyone, one of them should be carried away by the water. The other one should be heavy. Then we use this process of water or hydraulic washing. A heavy slope like thing will be there, like a slide. We have slides in school, no? That kind of slide like thing. At the top there will be a platform. On the platform, this ore will be powdered and put. Ore will contain impurities also, pure metals also. It will be powdered and put there, and water will be poured, sprayed or poured. When water is coming down the slide, water naturally flows down. When it flows down, the lighter particle, the dust is there, that dust will get carried away by this water and come down. Or if the ore is light and the impurity is heavy, impurity will stay there, ore will come down. Whichever is lighter among the two, between the two, that will flow down along with the water. The other one will stay there. So in this way we can easily separate the ore and the impurity. Third process is froth flotation. Froth flotation, it is useful for this. I'll put up the slide because diagram is useful here. Froth flotation as a process, it is done only for sulfide ores. Ores which contain sulfur. Okay, sulfide S. So if sulfur is there in the ore, galena, PBS, or mercuric sulfide, cinnabar, ores which contain sulfur, if you have that, then this process is very useful. A large tank is taken. Now when you see these pictures, don't imagine these are our small cups, beakers, etc. These are large tanks. They'll be as big as your water tank, or bigger than that also, because these are for tons of the ore, not kgs. Tons of ores will be processed at once. So they're very large ores. I mean, very large tank. So there is one huge tank here. In the tank, it is filled with water. This water will contain pine oil. Water containing pine oil. The water will contain pine oil. Why pine oil?
pine oil reacts with sulfur. Pine oil will, if sulfur is there in the ore, no, this pine oil will become froth, that is bubbles, and it will come floating on top. It will bring the sulfur on top. Now our ore contains sulfur. Ore is containing sulfur. Say we are trying this method on galena, PBS. So lead sulfide, PBS ore is there. It is having lot of impurities like rocks, small particles of sand, dust, everything is covered in it. So it is powdered. All of them are powdered together. We are having a mixture of galena ore. We are having this powdered sand, mud, everything is there together. That is poured into this tank. That powder is poured into this tank. So this pine oil, it will react with all the sulfide particles. That means galena, PBS is there. That PBS and pine oil will react and it will become like bubbles and it will come on top. So the ore will come here and whichever is not having sulfur, mud, sand, etc., they will settle at the bottom. Now from this we will pass compressed air inside. Why we pass air? You might have seen nowadays we make cappuccino coffees, foam coffees we make. If you go on beating it or if you go on giving air to it, no, the foam keeps rising upward. So as you go on pumping air into it, the foam keeps rising up and this will become your ore with lot of foam. This foam is separated and that contains our galena or lead particles. So the impurity remains in this tank only. This part, it is collected into another tank, or it is a pipe will be fixed here, like an opening drain will be there, so that this part will flow into that other container which will have all the ore. So this is a method of separating sulfide ores. In the froth flotation tank there is water containing pine oil. Then the ore is powdered and sulfide ore is powdered and poured into that water. Compressed air is passed. The sulfide reacts with the pine oil and floats on top as foam, while the remaining impurities, which are heavier, settle at the bottom. Thus, the floating sulfide ore particles are removed into another container from which the process continues. Thus, we separate sulfide ore or the ore from the impurities. This is froth flotation. Okay. The next one is magnetic separation. Now, magnetic separation is used for substances that contain, ores which contain iron. Now, this is any ore which contains iron, this method can be used. It contains two wheels with the conveyor belt. You might have seen this in grinding mills. If you give wheat, they make wheat flour, and give rice, they'll make it powder. They will have this kind of system. Two wheels will be there, one belt will be rotating around them. Here it will powder and it will flow through this and come and fall into the container. This is similar with a slight change here. Two wheels are there, one belt is there here. From this container, the powdered ore falls here. This is your non-magnetic wheel. The back wheel is the non-magnetic wheel. Front wheel is your magnetic wheel. So what happens here? This belt will carry the powdered ore to this portion.
whichever is not magnetic, the particles which are not magnetic in this, those particles will not be attracted by this wheel. So they will just go and fall directly. While those particles which are magnetic in nature, they will get attracted to this wheel and they will go till the last possible point. From here they can't come like this, so they will fall into this container. So two wheels, one is the non-magnetic wheel at the back, the front wheel is magnetic. The powdered ore is poured here, and with the help of the wheel they will go to the front. This generates kinetic energy for both of them. To be able to come and fall, it generates the energy. That is why this belt is required. So a non-magnetic particle, when it comes here, it simply flows and falls away from the wheel, and it falls into this container. The magnetic particle goes with the wheel till the last point and then drops into another container known as magnetic particle. So this way we can separate the magnetic ore from the non-magnetic impurity, or the non-magnetic ore from the magnetic impurity. Depends. If iron is the impurity in the ore, then magnetic impurity. If iron is the ore and some other impurity is there, then non-magnetic impurity. So it depends which is which, but method can be used when either the ore or the impurity is magnetic and the other one is non-magnetic. What are these four processes, by the way? These four are processes of dressing or concentration. What happened by these four processes? The impurity like dirt, dust, etc. got lost. They were removed. What we are remaining with? Pure ore. It will still have some dust. Like say sweeping, you swept your room. You have finished cleaning of the room in one way, but it is not 100% clean till now. You may still have dust at some corners. It might be say you clean the floor and all, but you have heavy cupboards or cot or bed is there. Behind it, under it, there will still be dust. It's still not completely clean. So your method is has reduced the impurity, but it's not 100% in pure form. Plus, the ore itself is chemically mixed with something else. Galena we were talking about. It is Pb and S. We want lead. It is still combined with S. But this PbS was covered with many other things. Those other things you eliminated. So maybe some part of it is still left inside. But if the impurity were say 20%, about 18% is gone. 2% might be trapped somewhere. This PbS, from this PbS, S has to be separated and Pb has to be extracted. That involves chemical processes. These are reductions. We have four kinds of reductions. But these reductions depend upon which type of metal it is. Here comes reactivity series. So we have something called reactivity series. What is a reactivity series? What is reactivity series? Are all metals of the same reactive nature?
No.
Which is the highest reactive metal?
Aluminium?
Did you read reactivity series? Textbook you have reactivity series, that is important. You have reactivity of I think 14 metals. 14 metals. The most reactive element is potassium. Potassium, sodium, aluminium, magnesium, calcium. High reactive. Okay, 5 metals of high reactive are potassium, sodium, aluminium, magnesium, calcium. And And don't think that this is the only reactivity series. You have 120 elements, means all 120 elements are there in the reactivity series. We are studying about some 14 elements in our 10th class syllabus. That I am showing you. Okay. This is reactivity series. Potassium, sodium, calcium, magnesium, aluminium. Once see your textbook, you will have these 15 elements. Aluminium is third or fifth?
Fifth, ma'am.
Fifth only.
It's not fifth only.
Okay. Potassium, sodium, calcium, magnesium, aluminium. Okay, 5 elements. Then you have 4 elements in mid reactive: zinc, iron, lead is there, no?
Yes,
Lead
ma'am.
and copper. Lead and
Copper only there, ma'am.
copper only. Okay. Zinc, iron, lead and copper. And then you have 4 elements in low reactor: mercury, silver, gold, platinum. Okay. So 4, 4, 8 and 5. 13 elements reactivity is there for it. These 13 elements in order we should know. We should know them in order. This is the reactivity series of metals. Low reactive, moderate reactive, high reactive. Under low reactive you are having copper, mercury, silver, no copper. Okay, copper you have in moderate, no? Mercury, silver, gold and platinum. Under moderate we have zinc, iron, lead, copper. Under high reactive we have potassium, sodium, calcium, magnesium, aluminum. So this is number 1. Potassium is the highest. Okay, potassium is the highest. Now you can learn these in this way: low reactive, moderate reactive, high reactive, to remember them easily. But overall, these 13 elements order we should know. Why? If there is a reaction, if there is a reaction, high reactive element can displaces low reactive element. I didn't write moderate here because if I am comparing potassium and sodium,
if I am comparing potassium and sodium, then sodium is considered low reactive, potassium is considered high reactive. They are number 1 and 2. Even then, potassium is more reactive than sodium. Okay, what is the meaning of this? We have reactions called displacement reactions. Displacement reactions. What is displacement reaction?
The high reactive
Suppose,
metal will displace the low reactive metal.
suppose we have KCl and sodium. KCl and sodium Na. Suppose we have KCl and sodium, and we have NaCl and sodium. What will be the product? Now, displacement reaction, what does it mean? Till last year we have learned displacement reaction. What does displacement reaction mean? Suppose we have copper sulfate. Last year's copper sulfate plus iron. In copper sulfate solution, if you put iron nails, what happens is we will get iron sulfate and copper will come out. So this here Fe and this SO4 joined together and Cu came outside. Okay, this is called displacement reaction. Now similarly, what will happen here? You tell me, if KCl and Na reacts, what will happen?
Ma'am, no reaction will take place.
What will happen if NaCl reacts with K, not Na?
KCl plus Na.
So here we will get KCl and Na. But here the reaction is not possible because sodium is less reactive than potassium. That's why this order we should know. If the element is below, it cannot replace the element above. Calcium cannot replace potassium. Magnesium cannot replace potassium. So if I have MgCl2, MgCl2 and Na, now the reaction result is MgCl2 is below, sodium is above. So can sodium replace magnesium?
Yes, teacher.
So what will be the answer?
NaCl plus Mg2.
Not Mg2, NaCl plus Mg. Now then we have to balance it. 2 NaCl will come. Means here 2 will come, here 2 will come. 2 Na and 2 NaCl will come. I am not putting the balancing factor right now. But here balancing it. We have to balance it. So just this is possible. The reverse, is it possible? NaCl
Mm.
and Mg. Is this reaction possible?
Mm.
Not possible because magnesium is low reactive compared to sodium. This reactivity we will be able to get from this reactivity series. Okay. Always remember, a more reactive material can displace a less reactive metal. If
less reactive metal is there, and it is in the reaction it is coming to displace the more reactive, that reaction will not take place at all. Examples are these reactions do not take place. If sodium has to displace potassium, magnesium has to displace sodium, that reaction impossible, it will not be able to do it. Okay, then with this we have a question. Let me check if I get the question today, or by Sunday I'll explain that question. Okay, so these, using this displacement, some reduction methods are there. Now before that, these metals like which are high reactive, K, Na, Ca, MgAl, they are high reactive. That means in the earth you will never find them in free state. You can never find potassium, sodium as it is in the earth. It will always be in some combined form attached to something else. But gold, gold we will get as gold only. Maybe it will be covered in dust, but it will not react chemically with anything. Silver also, with very few elements it reacts. Platinum also does not react with anything. Copper next. So if the metal extraction is for platinum, gold, no, then they are low reactive elements. They do not require that many chemical processes. Refining part is quite simple for them. Moderate reactive, they require some process, but they may not require too many processes. For low high reactive, we have to use refining method, electrolytic methods. Electrolytic reduction or electrolysis method is necessary because they are too reactive. Once, like if you remove one impurity, they may react with oxygen or water in its surrounding and become another compound. They are that much reactive. So generally, they require electrolytic reduction or electrolytic refining processes for final purifications. So mostly there are electrolytic methods for high reactive elements. For moderate reactive reduction process, refining, for anything we can use electrolytic, but it's not required in case of low reactive elements. Okay, these methods only are given in that chart for you. Which method is useful where? First, for moderate reactive. For moderate reactive, the ores will form oxides or sulfides. The ores may be oxide ore, they may be sulfide ore. So if it is oxide ore, it's the refining process is easier. So generally any ore is converted to its oxide ore before we complete the process. Refining process, before taking it to refining process, whatever ores are there, they are brought to their oxide forms. What I mean is, suppose you have MgCl2 or MgSO4. You have MgSO4, magnesium sulfate, magnesium carbonate, MgCO3. From these, by some chemical process, the ore is brought to MgO form. This MgO is sent for electrolytic refining. Magnesium is high reactive, so it will require multiple steps. First, it is converted to MgO form. From MgO form, it is converted to magnesium, pure magnesium state. So it involves two steps. Okay. This process of separation has, one is oxidation, one is calcination. Which process is used? Oxidation, sorry, not oxidation. Converted to the oxide form, we use either roasting or calcination. So what is roasting and what is calcination?
Ma'am, roasting is a process which takes in presence of oxygen.
Hmm.
Calcination is a process which does not require oxygen in its reaction.
What is done? Oxygen is needed or oxygen is not needed. Why? What are you going to do there?
Heating it?
Heating it. So the process of heating it, the ore has to be heated. High heat, extreme temperatures. So they are all called pyrochemical processes. Pyro means heat. Pyro means heat, and that too large amount of heat. Okay, high temperatures. So when we heat the ore at high temperatures, if oxygen is present or oxygen is necessary, it's roasting. When oxygen is not necessary, oxygen without oxygen the process can continue, it is calcination. Okay, roasting and calcination. So for which ore roasting is done? Roasting and calcination, we have two or three differences. Roasting is generally done for sulfide ores, and calcination is done for carbonate ores. Okay, CO3 carbonate which is there, for it we do, carbonate is present, we do calcination process. When it is sulfide ores, generally roasting is done. Okay, so what happens is the sulfur which is there in the ore, that sulfur will become SO2 or sulfur dioxide or something and leaving the oxygen with the ore, and magnesium sulfide or magnesium sulfate will get converted to magnesium oxide. Same way, if magnesium carbonate is there and you heat it in the presence of, in the absence of air, without air or without oxygen, if you heat it, carbon dioxide will go away, leaving MgO, MgCO3, magnesium carbonate. When you heat it without external oxygen, CO2 will escape, MgO will remain. So these ores, they both give magnesium oxide in the end. I am giving example of magnesium. For any ore the same process is done. If it is sulfide or carbonate, they will come down to oxide form. For sulfide ores we use roasting, for calcination is done for carbonate ores. Okay, this is done in the presence of oxygen, that is done in the absence of oxygen. Give one example for each. Sulfide ores like galena, cinnabar, etc. Magnesium sulfide, magnesium sulfate, this method can be used. And carbonate, that is calcination, can be used for any carbonate or MgCO3, CaCO3, Epsom salt, etc. Okay, so write 2 points and give one example for each, which ore. Now after roasting or calcination you will get the oxide ore, MgO will form, magnesium oxide. This magnesium oxide undergoes reduction process. Okay, reduction is electrolytic reduction. We pass it through current. We put two electrodes, positive and negative electrode, and put the magnesium oxide ore inside liquid form. Then we pass current. When we pass current, what happens? Whatever is the cation, it will go towards the negative electrode. In magnesium oxide, magnesium is the cation. Mg plus will be there. It will become Mg plus, magnesium plus cation. It will go towards the negative electrode, and oxygen, O2 minus. So it is the anion which will go towards the positive electron. In the liquid, one will be the cation. It is positive in nature, so it will go towards the negative electron. The other one is the anion, which is negative in nature. It will go towards the positive electron. This way, they both will separate. Okay. So Electrolysis process is this one. Electrolysis process is this simple thing. We have a container where there is one positive and one negative electrode. We put the liquid inside, the ore as liquid inside, and pass current. When you pass current, that liquid will become cation and anion. Cation goes towards the negative electrode, anion goes towards the positive electrode. With this process, different electrolytic reduction refining, you have, I think, about copper sulfate. In textbook, you have copper sulfate electrorefining. In copper sulfate, in refining process, we apply some tricks to help it be more beneficial to us. Okay. Then the reduction process, 4 or 5 are there. 4 reductions are there, I think. Auto reduction or self reduction, displacement, and electrolytic reduction is there. One more is there, I think, by heating. So once I'll see the textbook, reductions and refining, difference I'll tell you. What you have, I'll tell you that. Now, these are some 8 processes are there here. Liquation, polling, blister copper method. What is that? That is polling, yeah.
Distillation,
Yeah,
electrolysis.
distillation and electrolytic reduction. These 4 are there. Distillation. And in refining, 4 methods of reductions or refinings are. So these are 8 different methods. Today what methods I have covered in reactivity series, learn them. These 8 methods I'll explain separately. Last one is metallurgy of iron. Blast furnace. What is a furnace? Furnace is basically, it's a huge building. And this image is what an industrial furnace looks like. Okay, see this. This is how your industrial furnace looks like. It's basically a very huge building downward. From here, this is the top floor or where people work. They throw what is required inside, and at the bottom, some 2 floors below or 3 floors below, the material comes out. So basically, it is a large structure. But like this, if we see, we can't exactly say what is happening there. So we learn the schematic diagram of a furnace, a simpler form of furnace we learn and see. Can you see this? If I click here again, something will come. Can you see this? It's like this. People work here. This inside here, we will have the furnace. So industrial furnaces are very, very huge. But this way we can't explain what is going on. So we learn it in the form of schematic diagrams like this. So what happens here? This is blast furnace. Blast furnace is used for the iron ore. This is a very thick wall building. It's made of very thick bricks, 2, 3, 4 bricks. Sometimes it even goes up to thickness of 1 meter each. On each side it will be 1 meter, because inside the temperatures are very, very hot. It goes up to 3000 degrees. So 2170 is given here, but sometimes the temperature even reaches 3000 degrees. So it's very hot. That heat should not come everywhere outside. So this outside layer insulation will be very thick walls. At the top here we put these charge, iron ore, limestone, coke. Charge is the fuel. Okay, what fuel is required, those are put inside so that it will start burning. That coke is our reduction agent here. For reducing, we need coke that is purest form of carbon. It's coal from which all the oxygen is removed. Then impurities are removed, not oxygen. All the impurities are removed, so it is the purest carbon. Limestone, CaCO3, calcium carbonate, and iron ore. So if it is Fe2O3 or Fe3O4, hematite, magnetite, whichever ore, iron ore, limestone, CaCO3, coke, pure carbon, and the fuel required. They all go into this charge. Hoopers will be there. Through that they will be going into the blast furnace. Here at different temperatures will be maintained. That is, the top part will be around 500. As it goes below, the temperature goes on increasing. Here 4 reactions take place. 4 reactions take place as it is falling. Okay, I'll tell those reactions. So as it's one reaction, we can see here Fe2O3 plus 3 carbon, that is coke. They both will combine and it will become molten iron will come. Iron will come in liquid state. Carbon monoxide CO will leave. So this is the final reaction. This ore, which is in the form of Fe2O3, it became Fe, became iron Fe. Okay, this iron will be in liquid state and it will fall here. But iron is very heavy, even in liquid state it is very heavy. So that heavy iron will go at the bottom. And whatever other impurities are there here, now we didn't send only iron ore, we sent limestone, we are sending coke. So they also will form some other impurities. Some other reactions will take place there. Those reactants will come and fall on top. They won't be heavier than iron. So they will be up. Iron being the heaviest goes to the bottom. And from here iron is taken out from this outlet. These impurities are taken away from this outlet. So slag, all the impurities comes from one outlet and iron comes out from the other. To maintain the temperature here, from here and here, from here basically, hot gas will be pumped inside always. Hot gases will be pumped. Waste gases, which are like carbon dioxide, will form. That will come out from here. So this is our blast furnace. What happens in the blast furnace? We pour the charge, iron ore, limestone, and coke from the top. It's maintained at different temperatures. Iron ore becomes pure iron, sinks to the bottom. The impurities will float above it. One outlet will remove the impurities, another outlet will remove the molten iron. To maintain the temperature, we have an inlet from which hot air is blasted, and hot air waste gases will come out from an outlet. This is how blast furnace works. What are the reactions of a blast furnace? These are our reactions in the blast furnace. These are our 5 reactions in the blast furnace. First, what happens is the coke which you put inside, carbon, pure carbon, it reacts with oxygen and forms carbon monoxide. C plus O2 gives rise to CO, carbon monoxide. This carbon monoxide reacts with iron, Fe2O3 and CO. They both react. Fe will form, iron will form. This is the main step. We want iron, so iron will form. CO and O will become CO2, the waste gas. This gas will be removed from the top. Waste gas, it will go out. Now, this reaction, it Fe2O3, this happens at very high temperatures. Fe2O3 plus 3CO gives you 2 Fe and 3 CO2. This happens at very high temperatures. If temperature is not very high, if it is low, then it will form this Fe3O4 at lower temperatures. So this should not happen. The second reaction should not happen. That is why the temperature is maintained above 2000 degrees centigrade. Why such high temperature is required? Because if temperature is low, then it will form another ore. It will not give you pure iron. So that is why temperature is maintained at this one. So these are the first two reactions. Now along with that, we also put calcium carbonate or limestone. Why did we put limestone? To remove impurities like silica. SiO2 will be there. Sand might be there. To remove this sand from the iron ore, we put limestone. What happens to limestone? At the heat, whatever temperature is maintained there, 500, 600, 700 degrees, it will become CaO and CO2. First it will become CaO and CO2. Then this CaO and CO2, they will, the sand will mix with SiO2 and CaO, this calcium oxide. In the high temperature, it will react and form CaSiO3, calcium silicate. This calcium silicate is the slag we get. Now in the furnace, where was the furnace? Now in the furnace, first what happens is that iron ore, Fe2O3 and CO, this reaction does not take place in one step. It happens in two steps. First it will react with, like, carbon reacts with coke and oxygen. They react and they form carbon monoxide. That CO will react with Fe2O3 and become Fe, and CO2 will form. That CO2 will be expelled from here, it will go out. Then this limestone which is there, CaCO3, in these temperatures it will become CaO, calcium oxide. That calcium oxide will react with whatever sand is there in this iron ore and charge, which is there, it will react with that and it will form calcium silicate, CaSiO3. And that CaSiO3 calcium silicate will come here. The pure iron will go to the bottom. From bottom, pure iron will come out, calcium silicate will come out from here. Whatever CO2 gas forms, that comes out from here. So this has outlet for your ore, impurity, and the waste gases. That's how blast furnace works. Okay, now you have some more processes there. Heat process, which I said they are still there, reduction, those are there. And then you have, apart from those 8, smelting is there. Smelting is this only. Melting at very high temperatures is called smelting. That happens in your blast furnace. And then there is one more, reverberatory furnace is there. Working is not given, just diagram is there, how you can assume how it works. So some more parts are there in this chapter that I'll cover next class. Meanwhile, any other doubts are there? Specific doubts. Next week I think you have one more exam, no? From third or fourth. When is your exam? Okay, so what is the syllabus for that?
Essay one portion.
Okay, essay 1 portion. Then all this won't come. Essay 1 portion means 1 to 6 only.
7, ma'am.
7 is also there. Okay, 1 to 7. Okay, anyway, if any doubts are there in that, ask on Sunday. 1 to 7. Okay. In this, some more topics are there that I'll cover on Sunday. Sunday I'll tell you what time. Morning may not be possible. If it's not possible, then 4 o'clock I'll tell. Okay. Okay. See you. You can leave now.
Thank you, ma'am.
Welcome.
Thank you, ma'am.
Thank you, ma'am.